Session one was about the basics, if you like, of the energy systems. And you had engineers, you had scientists. We've got a full selection right across the sort of academic range for you now. And I'm going to kick off with Gavin Bridge from geography, and follow up with Adrian Green from history. And then we'll get back to the science faculty with Frank as the third of the three speakers in this session. It's all yours, Gavin.
Well, good morning, everyone. Can you hear me? Yes, great. Well, it's a pleasure to be here. Can you put it on? Switch it on. Really? Is it switched on? I believe it's switched on. Oh. Is it orange or white? Orange. Okay, thank you. That's great. Okay, so it's a pleasure to be here. As John says, I'm a geographer. I'm an economic geographer. And if there's one thing you know about geography, it's that we're interested in space. We're interested in the relationships between places on the globe. So I want to talk to you today about liquefied natural gas. So there's something interesting going on in the world of gas, and that in order to get gas to move across space, we can do a number of things to it. Principally, the problem with gas is getting its energy content dense enough so that it can cross space. So there's three things I want to do today. I want to tell you what liquefied natural gas is, and then I want to try and examine a little bit some of its significance, how its significance goes beyond its role as a technology. And I'm going to be alluding in particular to the way it connects up gas markets across the world, and suggest that we're at a key moment in the making of a global gas market. And the punchline is that gas is becoming more and more like oil. And the final thing that I want to do is to try and anchor that a little bit in a case of the UK and show what role LNG, liquefied natural gas, has in the UK. All right, so first of all, what is it? Well, it's very simple. It's taking natural gas and it's turning it into a liquid. So it's a physical change of state from a gas to a liquid. How do you do that? Well, you do that by cooling it down a long way, down to minus 162 degrees. That's very cold indeed. And when you do that, you reduce the volume of gas. And people who like to talk about this describe it as taking a beach ball and reducing it in size to a golf ball, a 600-fold reduction in volume. So if you think about what's going on there, you're taking the same energy content and you're packing it into a much smaller space. So simply put, you can pack a lot more energy into a fixed space. You can put a lot more energy onto a ship to get it to cross ocean space if you chill it down. You can get 600 times the amount of energy in the liquid state as you could in its gaseous state. And that's important because it means you can overcome the friction of distance. You can make it commercially possible to move gas across ocean space. Now, LNG itself's not new. It's been around for around 100 years as a technology, but it's principally been used in the past for dealing with temporal, time-based differences as a way of storing gas between moments of surplus to moments of a peak in demand. So a series of plants have been built in gas systems around the world that do the work of peak shaving. They sit there as a reservoir of energy that can be brought on stream at moments of peak demand. In terms of moving gas across space, there were some early developments around 50 years ago. Here's a picture of a ship called the Methane Pioneer. Natural gas is predominantly methane, and this ship took gas from Louisiana, the southern states of the US, and brought it into the UK, into Canvey Island, outside London, as part of an experiment by the British Gas Board to diversify supply. It really wasn't a commercial operation. It was a kind of technical demonstration of proof of possibility. But since the 1960s, LNG trade has taken off, and I'm going to suggest in a few moments how it's transformed. The point would be, though, for most of its history, until recently, the trade in liquefied natural gas has been very limited in scope. So here's how it works. This is based on some field work that I was involved in with some colleagues. And the example here is that if you take the top left, this is an offshore gas field, and it's in Qatar. So Qatar in the Middle East, if you think about your basic school geography, Qatar is that thumb-like projection that sticks out into the Persian Gulf. Offshore Qatar, opposite Iran, is a very large gas field. And that gas is brought on shore in Qatar, where it is liquefied, the top right. These are basically very large refrigeration units. They sit there in 45-degree heat, chilling gas to minus 162 degrees to get that reduction in volume. In its liquid state, it's then put on a ship, the bottom right here. This is the tankers at Ras Laffan on the coast of Qatar, and it sets sail. If it's coming into the UK or Western Europe, it takes about 10 days, comes through the Suez Canal, and the gas on that ship in its liquid form, chilled down to minus 162, is not additionally cooled on the ship. It is just thermal mass that keeps it in that state. So 10 days, it comes through the Mediterranean, up the west coast of France, of Spain, past France, into the UK. And the example here would be at South Hook, near Milford Haven, the bottom left, where it is regasified. It's expanded again, basically warmed up, expanded and pumped into the national transmission system from where it can be distributed across the UK. So the significance of this technique is that it enables gas to be moved beyond the end of continental pipelines. So as a geographer, I'm interested in that because I'm interested in where gas moves in the global economy. And for most of its history, gas has been limited to the extent of pipeline networks. But here, by converting it into a liquid form, it's possible to move it either in these large tanker trucks beyond the end of a pipeline, for example, into the interior of a continent, or to put it on a ship and make it cross ocean space, to connect up what were formerly separate pipeline systems. So here's a set of figures. There's a lot going on this graph. If you just focus on the green blocks at the bottom, so we've got time across the bottom, and you can see here the green blocks are expanding over time. That's the total amount of LNG in world trade. So we can see it's basically doubled since 2000. Today it's up around nearly 300 million tonnes a year. You might say, is that a lot? It's about 10% of global gas trade. So it's not the majority. Most of the gas that moves across national borders is in pipelines, but it's a growing proportion of that total flow is in this liquid form. The red lines show the number of countries that are in the business of exporting gas, and you can see that that's doubled since 2000. And the blue line shows the number of countries that are interested in importing liquefied natural gas, and that's quadrupled since 2000. So in simple terms, there's an interesting story going on here. There's a new gas economy taking shape around LNG. And the point is that it is transforming world trade and the way that gas gets bought and sold. So I'm going to show you two maps. I'm a geographer, it comes with the territory, I'm afraid. So here's a basic map from 2002. LNG trade in that period was around 100 million tonnes. And if you look at this map, you can see a couple of basic things. One is there are some connections between areas of export, areas of import. And there's really three areas on the map. There's a little bit in the Americas, there's quite a lot between North Africa and Europe, and there's quite a bit more in Asia, and particularly from Malaysia and Indonesia into Japan and South Korea, with some outliers in Australia and Qatar and Oman, supplying into East Asia. The principal market for liquefied natural gas in Asia is Japan. Japan is an island, it doesn't have any domestic gas resources, and gas is a very significant part of their energy mix. And most of it all of it arrives in a liquefied form. So fast forward to a bit closer to the present, and you can see how this trade has transformed. So a comparison with the previous map, one simple thing, it's much more complicated. The size of the flows have increased. But if you drill down a little bit more, we can see some interesting things. If you focus on Nigeria and you focus on Qatar in the Middle East, you can see that these supply zones are now shipping both ways, across the Atlantic and into the Pacific. So you're starting to get the connection across these spaces. we can see that some new areas have come on stream in very significant ways. Australia, for example. And we can see for a region like Western Europe, the way in which Western Europe is being supplied through a number of different supply zones, a diversification of gas supply in Western Europe through LNG. Now, this map's a couple of years old, and if we were to update it today, there would be something else on there that is not currently shown, and that would be the North American story. I'm sure you're familiar, maybe from the news, of the idea of fracking, hydraulic fracturing for natural gas, and I think Andy Applin may have spoke about that in the first session. Well, the fracking story in North America has meant the US is now exporting gas. If it's exporting it across the ocean, it's in a liquid form, LNG, and there's quite a bit of that now entering Asia and entering Europe. And another aspect that's not on this graph is the story in Mozambique, East Africa. Very large reserves of gas have been discovered, and there are efforts now to sell that gas ahead of production. It's not being produced yet, but to sell that gas before production into parts of East Asia. So again, the story of LNG is connecting up a series of distinctive gas basins. So the final thing that I want to say is to try and draw this home a little bit and relate it to the UK. There are lots of different aspects of this piece, but I thought I would try and anchor it in maybe in the UK experience. So on the left-hand side here, we've got a comparison of energy consumption in the UK between 1990 and 2014, 25 years apart. And if you look at the bottom figure, it's roughly 200 million tonnes of oil equivalent in both periods. So over 25 years, British energy consumption is basically stayed steady, right? But the key part of this is the expansion in the role of these different, the relative roles of different fuels. You can see on there coal in green, gas in orange, and oil in red. And the big story is the expansion of gas and the shrinking of coal. So gas here has expanded to be around 40% of the UK's energy mix. A lot of that is pipeline gas coming from Norway and coming from continental Europe, as well as domestic gas from the North Sea and from parts of the Irish Sea. But an increasing proportion of it is coming through liquefied forms by ship. On the right-hand side, we've got to drill down into that gas consumption. It takes that little bit of gas and says, how is that gas used in the UK across the period 1990 to 2016? And what you can see is a bunch of colours that are fairly steady, but then this big purple bit sitting on the top that ramps up from the 1990s. And that big purple bit is electricity generation. So a big part of the gas consumption story in the UK is the way that gas is being attached to electricity generation. And my final slide is to give you a sense of the role of liquefied natural gas in that gas supply into the UK. So the UK gets a little more than half of the gas it consumes from outside national limits. Over half of it is imported. Around nearly 40% is from imports, both direct from Norway through a subsea pipeline through the North Sea, as well as through two interconnectors with Europe. But around 17%, it varies year on year, of gas supplies coming into the UK in this liquefied form. There are 3 terminals, 2 in Milford Haven in West Wales, 1 on the Thames at the Isle of Grain. And these are connected in some very interesting ways to these diverse sources of supply. And if you were to ask me, well, where does most of that LNG come from for the UK? There's one answer. Over 90% of it over the last 10 years has come from Qatar. So the gas dependency story around liquefied natural gas is really a reliance on one particular country, Qatar. There's diversification around that. We do get supplies from Norway. We've recently had a supply from Russia in liquefied form. But we've built a set of relationships that have a strong tie now to Qatar around our liquefied natural gas. I think I've used my time. I'll stop there. Thank you very much.
Thank you very much indeed, Gavin. We need to mic up Adrian.
Just find something to attach this to. Right, does that sound okay? Great. Okay, well, Gavin touched on the shrinkage in coal use in recent years, and we're obviously at the end of a cycle in coal use for energy. And what I'm going to talk about is the start, and in fact the revolutionary impact of coal use on domestic housing. In this region particularly, because of the Durham coalfield and a regional economy built around coal in the 17th and 18th centuries, which in all sorts of ways transforms housing, but also the larger national picture, and particularly by the 19th century when most households are using coal in Britain, the transformations which are social as well as material. Right. Now, the content of this talk comes out of a project I did with Charlotte, who you heard from this morning, with the Durham Energy Institute, and it's the research that we did on energy use in historic buildings in the Durham region that I'm going to illustrate some of the changes. But the big picture, which was in the abstract for this session, is that the adoption of coal for house fuel revolutionises domestic life in Britain. And from the 16th century through to the 20th century, burning coal was a primary means of heating the home. And that this had consequences for the construction and the layout of houses, which I'll show in a moment, and particularly the use of domestic servants to carry and clean. And I think it's seldom recognised how important carrying and cleaning up after coal was for households who could afford to pay someone to do that labour. And the upstairs, downstairs prevalence of domestic service in the 19th century follows in part from coal use. It's not just the social side of the house, it's also that coal mining, particularly in a region such as this, had byproducts. So brick was manufactured using brick earth taken from adjacent to the coal seam. So when mines were sunk, the brick earth was taken out and manufactured into bricks, particularly for the pit villages, but also for the brick in a town such as Durham. On Tyneside, coal is being used to make window glass. So the windows, as well as the brick of 18th century houses, comes directly out of the adoption of coal in the economy. So in all those ways, coal mining transforms the house. And this is part of a much larger process, which the economic historian Tony Wrigley has summarised in his studies of the history of the Industrial Revolution. And he identifies coal use in Britain as the key to the takeoff of the Industrial Revolution in Britain. And what Wrigley emphasises is as the result of using coal and eventually steam power, we move from what had been an organic-based energy economy, where all energy in the economy comes out of human or animal muscle, which in turn comes out of plant fibre and food, to a mineral economy, where the carbon has been captured in coal, and it's the burning of coal and creation of steam that transforms the economy. Wrigley's published several excellent books on this, most recently the one on the slide, and if anyone's interested in that, I can't recommend his work highly enough. Now, we are standing at the absolute centre of the coal industry in Britain, and Durham itself was transformed by the adoption of coal. So, apart from the castle, the cathedral and the stone churches, there is no medieval housing stock left in Durham. York is full of late medieval houses. Durham was entirely rebuilt in the 17th, 18th and 19th centuries, rebuilt in brick with glass windows directly from the coal trade. And this follows from the fact that we're sat in the middle of the Great North Coalfield. And the reason why the Great North Coalfield took off in the 16th century is demand for coal in London. House fuel, but also in fact industrial processes such as sugar refining on the Thames, means that coal is being transported from the Tyne and the Wear by ship to London. And that occurs really from Queen Elizabeth's reign onwards. And it would be easy to have a very sort of economically determined approach to this, that because people start using coal, that then has a whole series of consequences. And in some ways that's true, but it's also true that energy use is bound up with social behaviour, and the adoption of coal goes with changes in how people live, I would say, rather than being quite caused by a change. And this is a rather fancy way of making that point. Okay, this is the key slide, really, for the point I want to make, which is that housing in England changed in the 16th and 17th centuries from the medieval tradition of an open hall with a hearth burning wood on the centre of the floor in the hall. And in many homes, that single hearth would have been the cooking fire as well as the sole source of heat in the building. And the smoke went out through a louvre in the roof. These open halls were open to the exposed structure of the roof. And there was a very strong... does this have a pointer? Ah, that's fine. I'm going backwards. Okay, there's a very, very strong social use of space in these medieval hall houses. You enter through a cross passage, there's no strong sense of front or back, and there's a very strong hierarchy moving up towards what was called the high table, these large windows lighting the high end of the hall. You usually have a bench here for the head of the household to sit behind the high table, and then servants and so forth sit below the fire. And then the solar or chamber is off the high end of the hall. And all social groups, from the court all the way down through the aristocracy, down through the yeoman, the husbandman and so forth, whatever size of household, they use the same social space. When chimneys are introduced, that goes with a transformation in the use of space. And the hall tradition disappears, except for in places like the Bishop's Castle in Durham or college halls in Oxford and Cambridge. Most households move away from the open hall, they insert a chimney, and in inserting the chimney, this tradition of the use of space disappears. And in its place, there is a ceiling, there's complete use of upper floors, and there is greater segregation of space, i.e. more rooms, and more rooms with individual fires. Before this period, it was only really the monasteries, the monks in the monasteries had individual fireplaces. After the Reformation, far more widespread in English homes to have many rooms with their own fires. So this alters the social relationships, and it also alters the material form of the house. So, as I say, with the industrial economy and the creation of brick and glass from coal use, as well as the heating source, this means that the house is involved in industrial production, and in fact the house becomes commodified, and houses increasingly are bought and sold for anyone to occupy rather than being created for a specific household. So we go through the medieval to the industrial period with a very profound shift in the use of space and the character of the house, which is bound up with the adoption of coal. And obviously, if you start burning coal, you do not want an open fire. You need to enclose it within a chimney to control the smoke. Coal is in line with a great expansion in the population in England over the 16th century, and its urbanisation, the cities which are driving this demand for coal, and indeed some shrinkage in access to timber and firewood. On Tyneside, the coal is being transported down to the river on these wagons, and there were wooden wagon ways, wooden wagon rails coming down the hillside, gravity-fed, and then taken back up to the mines with the pit ponies. This is a ship taking the coal away for export, and here in the background is a glass house using the coal on Tyneside to manufacture window glass. In addition to the human factors, population increase, growing towns and cities, there is also an ecological context for this, and it's now recognised that the great take-off in the use of coal and the introduction of chimneys into English houses is precisely the time of cooling in the natural environment, and this is what's known as the Little Ice Age. Contemporaries, of course, weren't aware that they were responding to a climate change particularly, but over the generations when this cooling occurred is when we see the take-off in the adoption of coal. And as I say, that's part of a much larger economic transformation and the onset of the Industrial Revolution. Okay, this is a house on the Bailey in Durham near the cathedral. It's actually now the history department where I work. And this building, built in the early 18th century, is a very good example of bricks made in association with the coal mining and window glass made in association with the coal mining. Not only that, even the tallow for candles is directly related, in this region at least, to the coal economy, because the tallow for candles is a byproduct of animal production, and the animal production, particularly sheep and dairying, is to raise food for the industrial workforce on Tyneside. So you get in this region a very regional economy which turns on coal and affects even the lighting of the house as well as the glass windows and so forth. The project I did with the Energy Institute looked at a very well documented gentry household for Judith Baker, who occupied this house, Ellamore Hall, just outside Durham. And her household accounts, that's the plan of the house, her household accounts show the costs of energy use. And it's not just the coal itself, it's the chimney sweeper, the servants, coal tax, and so forth. That's the summary. So we included cost of candles, cost of clothing of servants, cost of direct payments for coal, turnpike charges for carrying the coal, window tax, which is a tax on obviously housing, and the servant cost. There was a very strong seasonal dimension to this, which partly relates to the closure of the coal trade in the winter months and a dip in the high summer. And I've made this point, but I think this is one of the most profound changes, actually, is the impact on domestic service. Okay, so just to summarise, repeat the points. Energy use is integral to social practices and how we behave in buildings, and it's a relationship between people and their material infrastructures. And that the adoption of coal for house fuel transforms the house socially as well as materially over the 16th to the 19th centuries. Particularly the introduction of chimneys to control coal smoke, which in turn enables the creation of many separate fireplaces and the greater specialisation of room use, far more rooms with particular purposes. Servants to carry and clean, and in a region such as this at least, glass and brick manufacture related to the coal trade. And so if you think it transforms how people experience the house in the evening, for example, sash windows, mirrors to reflect light, tallow candles mean that people in the 18th century start using the home in the evening in a new way. And one could point to all sorts of ways in which the social practices of the house are transformed. And this occurs in a regional context, but also in a national context. And that's what I wanted to say.
Adrian, thank you very much indeed. Well, we've looked at past energy use with Adrian, present in part with Gavin, and it's probably appropriate that our one PhD student speaking today, Frank, should look to the future. In fact, I'm tempted to borrow from Noddy Holder and say, let's look to the future, it's only just begun. Frank.
Hi, so I'm a PhD student. I look at materials and how we can use them in fusion reactors. So we're all familiar with one fusion reactor, our sun. So what it does is it fuses together light elements to produce heavier elements. So I could argue that the sun and all our stars are the building blocks for life. So they come together, fuse heavier elements, and then they explode and send out this material all over the Earth and all over the universe. So we're all part star. But I'm more interested in how we can use this to make power. So the first reference to fusion power is the Zeta machine. And this is in Harwell in Oxfordshire. I thought I'd put a picture of some people in suits and ties. And this is from the 1950s and 60s. And it produced neutrons. So I'm going to try and explain how the production of neutrons made them think they'd produce fusion power. there was some skepticism about the results, and essentially they retracted the claims. But the important thing to remember here is that fusion was no longer private and classified. It was public, and it hit the newspapers. So we've got a son of our own, made in Britain, and it's for peace. And also we've got from the Daily Mail, reputable newspaper, right? The mighty Zeta, limitless fuel for millions of years. And arguably, fusion is still sold by this method. Limitless fuel, millions of years, peaceful, but also it can provide the base load. So a lot of the discussion previously about renewables is the solar power won't work overnight. It's not always windy. Nuclear fusion, in theory, would provide the base load. So when fission reactors come offline, we have something else to replace them. So this is some more recent news. So this is from The Guardian of March this year, and then from The Times and Nature. And essentially, there's one company, MIT, their Plasma Science and Fusion Center. They're going to build a multi-million-dollar collaboration to develop fusion energy. And everyone says fusion energy is 30 years away. So they've said we're going to get it on the grid in 15 years. One of the arguments that counters this 30 years away is it's 30 years worth of funding away. So once they realized you couldn't weaponize fusion energy, then the money dropped out. You can clearly see this in some data. So the other thing to consider is we have a number of different players. So we have this project called ITER. I don't know if anyone's heard of it. It's an International Thermonuclear Experimental Reactor. And you can see that China, EU, India, Japan, Korea, Russia, and the USA are all investing in this. It was developed in sort of the 1980s. The design was completed in the late 1988. And it's taken about 40 years to build. And it's worldwide. And it's huge. And it's costing about 20 or 40 billion dollars. So that's quite a bit. Each country has their own part. So I'm working for Fusion for Energy. So this is the European leg or domestic company. But MIT is looking to make something smaller, privately funded, affordable, robust, and compact, which is their spark reactor. It also happens to appear in the Iron Man movies, if anyone's seen. So they're sort of pushing for the fact that we need smaller generations, so there's less capital cost. And we have a company in the UK called Tokamak Energy, and they're based in Oxfordshire, and they're developing fusion energy. So they're in the research and development stage at the moment, so they're expecting power plant production by 2020 to 2030. And then we have companies like General Fusion, who are based in Canada. There's a lot of international things, like Korea has K-Star, and Japan has JT60SA. There's loads of fusion energy going on. Oh, I forgot to mention JET. So the UK also set the world fusion energy record. They produced 16 megawatts in 1997, and that hasn't been surpassed. So that's the joint European Taurus. So it's going to be great when we leave Europe. So here's a few of the basics. I don't know if you've heard of deuterium and tritium. So these are the fuels. So it's a hydrogen atom, but it's got more neutrons. So there's 2 here, and there's 3 in total on this side. We essentially get them really hot, combine them together, and you end up with helium and a neutron. So if you've got a neutron, you think you've produced fusion power, but in the case of the Zeta, they hadn't. The thing that's important is we get energy out. So we've seen this equation already today, and you should all be familiar with it. E equals mc squared. So what does that mean? We're looking at a change in mass between the reactants and the products, and c here is the speed of light, which is 3 times 10 to the 8 meters per second. So if you square that, you get a massive number. And we're all familiar with fusion power because we've seen Hiroshima. It's the same technology. The thing that often is attacked by fusion is it's not currently commercial. So if I take the cost of ITER and I take the price of electricity and I divide those 2 numbers, I see that it's going to take about 1,800 years to pay back. Okay, so I think solar panels are about 10 years, wind turbines 10 to 20. There's a number of problems with the design of ITER. Essentially, it was done in the 1980s. We've moved on quite significantly since that time. And also, it's technologically complicated, and there's material science. So there's a lot of things we're not familiar with, but in the future, we'll develop the skills. So one of the things about the plasma is that it's really hot. It's 15 million Kelvin. How do you handle something that's 15 million Kelvin? Very carefully, it's a good answer. So if you're a star, you just use gravity. There's so much mass that you hold in the plasma using your gravity. We can't really do that on Earth. Another attempt is to use inertial confinement. So we have these really small pellets of fuel, and then we fire the most powerful lasers in the world at them, and we produce some fusion power. So this is from the National Ignition Facility. It's not clear how you're going to commercialize this. The amount of pellets you have to put in the machine is unfeasibly large. So the final and most commonly used method is magnetic. So essentially, we have this plasma, which is negatively charged electrons and the positive ions, and we confine it using magnetic fields. So you can see sort of a diagram here. We've got some D-shaped magnets, and we end up with this plasma circulating around. So hopefully, I can outline a few engineering challenges. So we've got this 15 million degrees, which we're going to handle very carefully. We need to generate these magnetic fields efficiently. So we all should know that if you put a current through a length of wire, you generate a magnetic field. We need to understand the effect of the neutrons. So if in every reaction we produce a neutron, we're going to massively affect our materials. And obviously, the key element here is to generate more electricity than is used to fuse the fuel. So I mentioned jet earlier. That's at the world record. It still didn't produce more than it consumed. So we're trying to net produce energy. Otherwise, this is a rabbit hole. So I thought I'd show you some of the figures from recent work. So this here is the toroidal field magnet. You can see the group of people inside of it, just to give you a sense of scale. And I've written that there's 164 million amps is used to generate the magnetic field, which is just, I thought I'd just put some big numbers on. So this here is the ITER system, and you can see sort of the ear-shaped D magnet here. And there's all the people inside of it. So to get 164 million amps through a length of wire, you need to make it superconducting. And this is my supervisor's favorite fact. Once we've established this superconducting system, we have the largest temperature gradient in the universe. We have something which is at minus 269 degrees Celsius, next to something that's 150 million Kelvin, or 15 million Kelvin. So there's quite a problem with confining it. The other thing, and I don't know if it's clear with this laser pointer, is at the bottom of these Ds, we have this thing called the diverter. This will be clear on the next slide. So this is the diverter here, and I've put another big fact. So the heat load on the diverter is 10 times higher than that of a spacecraft re-entering the Earth's atmosphere. Right, so you've seen spacecrafts come into the Earth and burn up, or not burn up in theory. So we need to exhaust 10 megawatts per meter squared of heat continuously. And the entire thing is huge. You can see the man there for sense of scale. So we use tungsten, which melts at 3,700 Kelvin. But also we have high pressure water systems to keep it cool, so it doesn't melt. The next challenge is the vacuum pressure chamber. So this is double-walled, hermetically sealed. It's the largest stainless steel chamber ever built, and it's heavier than the Eiffel Tower. So it has 44 ports to allow for remote handling, operations, diagnostics, heatings, and vacuum systems. And on the bottom right here, we can see a person on that for sense of scale. We have the system that is building this vacuum chamber. So there's a few challenges of building something on this scale and size, and with this precision, hermetically sealed is tricky. So to stop you from worrying about fusion never happening, here's a picture of the ITER site in March of this year. If anyone's on Twitter, following the ITER organization is really interesting because they post some really interesting photographs. It's 50% completed. There's a number of buildings on site, and they've all been constructed. And here is the plasma hall, so you can see sort of this round shape, which is where the vacuum vessel is going to sit. And a lot of the problems is they're building the first of a kind. So here's the outline pathway to fusion, which is from the Eurofusion organization. So we mentioned jet earlier in 1997, setting the world record. This used copper magnets, so when you put current through copper, you have resistance, and this is why you didn't get any more energy out than in. In 2029, we expect the first reaction of deuterium and tritium in ITER, so that's 11 years away. So I'd like to think that's in most of our lifetime, but I'm not sure. Sorry. By 2050, we expect to build a demonstrator prototype reactor, which will demonstrate that you can generate fusion energy efficiently and on the grid, but the design is not yet finished. And then by 2075, we expect power plants to be online. So there's one aspect of it I've not really explained. The larger the magnetic field you produce, the more power you get out. So when we went from jet to ITER, we didn't change the magnetic field strength that much, but we made the radius larger. You can see that the power goes to the magnetic field to the power of 4. So a very small change is huge when you take it to the power of 4. So a lot of the research is looking at generating larger magnetic fields to confine your plasma and make the system more compact, because there's less capital to build. And also the idea is we could have modular components and economical to run. I think there's meant to be a talk on nuclear fission earlier in this session. Nuclear fission is also going in the same direction. Rather than building big things like Hinkley Point C, private companies like Rolls-Royce want to make small modular reactors so you can just standardize components and generate these things quite efficiently. That's it. Thank you.
Thank you, Frank. Thank you, Gavin. Thank you, Adrian. I'm now going to open up for questions, but before asking you to raise your hands, I need to service the ones that were sent in that we applied to session 1. So, Mo Brown, I think perhaps, did you ask your... You did, thank you. And Christine Latham? We'll supply written answers anyway, so Christine's not here. Bernard, you managed one of your two, I believe, is that correct? Would you like to ask the second one?
Thank you, Chairman. My question goes back really to the first presentation on, we saw transport of liquefied gas across the sea in these very large vessels. And going on beyond that, world trade has come about by the development of very large vessels. These are driven by diesel engines, very large, efficient diesel engines. And it's now cheaper to send stuff from China to UK than it is to deliver it in the UK. Yet we're being told that diesel engines should be phased out. Now, most of the world's trade is undertaken as a result of transport by diesel engines. When diesel engines are phased out, what happens to world's trade?
Gavin.
Thank you. It's a really interesting question. There's two answers. One, the first answer is around what might substitute for the existing diesel engines. As you point out, most of world trade is powered by diesel engines, these very large marine diesels. The reason that they came about was really to create value from the residues coming out of petrochemical refineries, the low-grade bunker fuels, and these machines can operate on these kind of very low-grade fuel products coming out of petrochemical refineries. So the direction, the direction of technological innovation is either to replace diesel engines with liquefied natural gas, and there are a number of ships up and running that do that. It's also to develop electrical fleet. Norway is leading the development of a marine electrical fleet. I'm a social scientist, so I don't fully understand the technical limitations of battery technology when it comes to shipping, but my understanding is that the kind of frontier of developing battery technology for shipping has expanded dramatically over the last five to 10 years. And there's another direction of travel in technological, which is a contemporary sailing, sail technology to augment, to supplement either diesel or gas-powered shipping. So that's one type of response to the question, which assumes that we will continue to have the pattern of world trade that we've had for the last 50 years. Of course, the more fundamental question is the existing space economy, economy of globalization, is underpinned by cheap fuels. We've arrived at that state as a result first of cheap coal, as Adrian pointed out, and more recently as a result of cheap petroleum in the form of diesel. And there's some really interesting work around the idea of deglobalization, or what some people are referring to as onshoring, the opposite of offshoring, which makes the point that the reason we have the existing long-distance trade in manufactured goods is because the costs of transportation have been driven down to such a point that businesses are able to choose their manufacturing location based not really on transport costs, but on differences in labour costs. So once the cost of fuel changes, if we internalise the external environmental costs, CO2 emissions, air pollution from diesel and from other fossil fuels, then the costs of transportation rise. And if the costs of transportation rise, it reasserts this friction of distance, and you'll start to see the onshoring of manufacturing. And there's some limited evidence, it's still limited, but there is evidence in the United States, for example, where you're beginning to see some onshoring of manufacturing taking place. That's occurring principally because of cheap gas, which is making it possible for manufacturing high energy intensive users to relocate into the US. But I think your questions are absolutely fascinating one. You either go the direction of assuming we'll continue to have these patterns of world trade, or you start to question, actually, was this one moment in time, the last 50 to 60 years, and actually we'll start to see a deglobalization. Thank you for the question.
Any other comment? No. I will then, if I may, pass to John Lloyd, who has a question which is appropriate probably for this session, but I'm looking around for Chris Spargo.
I've got to admit to being a fraud. I didn't frame this question and I don't even understand it. But I pass it on. Is any research or development being undertaken in the UK for the production of micro-generation facilities using vertical axis wind turbines with hydrogen storage?
Do we have the original? We don't know how the question. Okay. I did get. I put one penneth in, as it were, not even two penneth here. Certainly, there are research going on separately on both of those, hydrogen storage and vertical axis wind turbines. But I do have a comment from Chris, who was on the panel the first thing this morning. And he says, yes, separately, but not as a complete unit as far as I'm aware. But he also adds this research is linked to the integral facility in Rowlands Gill. I think we need to do a little bit of research to answer that question more fully for you. Just one or two, before we get on to the questions from the chair, if I may. Mo Brown, are you in the audience? Would you like to ask your question about tidal and so on?
I'm not sure that it's entirely relevant to what we've been hearing, though. I'll read it. Unlike solar or wind power, tidal sources of energy have a twice-daily certainty of supply. What objections lead to the lack of investment in tidal barrages, turbines, etc.?
Okay, we don't have researchers who've done a great deal of work on this area. I've got some part answers here, but I see that, John, you contributed one of those part answers. So, it's all right.
I did some work with something called the CGen tidal generator, which is based in Strangford Lough in Northern Ireland. And one of the major problems with tidal generators is simply really drifting into Gavin's field. There aren't that many places that actually have a strong enough tidal current that will provide significant, so to allow them to provide significant amounts of energy. So the CGen generator in Strangford Lough, which I will actually show in my talk this afternoon, was almost uniquely located because the tide in Strangford Lough is so powerful that you can generate a significant amount of energy from a tidal generator placed at that location. However, even with one of the strongest currents in the world driving your tidal generator, there was only still enough power being generated for a relatively small town. And given a lot of this, it's possible to make much larger tidal barrages, but we then start to get into environmental effects and cost benefit.
Please.
Right, the River Severn, put the outer barrage in, that's 8 nuclear power stations. Oh, if you believe the Department of Energy, the water flows for 3 hours. They're working on the river, the flow from the River Rance, where my father went 40 years ago. The only problem they had with that was that the oil seals went. None of the problems that you've had with nuclear industry. Now, that is the cheapest fuel, electricity fuel in France. It's paid for itself, the River Rance, and it's only got a limited flow. It's also a huge tourist attraction. Wonderful. So you're talking about that. If you're worried about the tide stopping, high tide, low tide, you then go and look at Dr. Price's research, where you put an extra barrier in, where you can drop the water, then you get mud flats perfectly good for the bird life, and then you can put something up at Solway. If you've ever read bird tide tables, they are at different areas, okay? The tides rise and fall at different areas, so you can use that. You can use it for energy storage as well. When you're generating nuclear power stations at night, you can keep it up there and then drop it, okay? Now, diesel engines, right? They're over 50% efficient. What are you going to do with the waste from those oil? Right? Where else are you going to use it? Yes, it is high in sulfur at the moment, and the engines they use are high in particulates and high in sulfur, because they don't remove the fuel, the sulfur fuel. Battery power, look, those diesel engines get 1 ton of goods, 1 kilometre, in, I think it's the energy from burning a sheet of A4 paper, right? It is approximately a cost of a first-class stamp in this country to get a ton of goods from China to us. That's the problem you've got to beat.
Yeah, thank you.
I could go on and I could comment. Like
we will
this, of course, I've been going to energy conferences for 40 years. No natural light, no reflectors on this. Yes, I have told the professor that this university is inefficient, and I have a brother who's an architect, and he agrees.
Two things. Thank you very much indeed. Two things. We will address energy density in my talk a bit later on. And I agree with you completely about not only this building, but the whole of the university infrastructure. And only yesterday, I think it was, we had the announcement that my nagging had got through, that we will start to behave in the way that we would expect others to behave in terms of the new build for the university. And Jackie, on my left, has been driving this as well driving it for us, that the future developments here, the buildings that are now being in the planning stage, will start to incorporate sustainability, appropriate measures in terms of insulation, light, and we will use them as a living lab so that we get better at what we're doing. So that, you saw the note yesterday? I'll pass it to you. It's actually come out of a consequence of the student body pressing the university to divest of any investments it had in the fossil fuel industry. Now, we don't really, and we've never had them, it's not the way we hold stocks, but that was taken seriously and to help the direction of change. But one of the things we obliged the university to do was ensure its own house was in order before it made proclamations about what other people should do. So it's coming a bit too late, but it is coming. Okay, Mo Brown, you had another question on Craigside, I believe.
Yes. Do you want me to ask?
Yes, and then we'll open it up a bit wider, if we may.
I'll read it. Could it be done like Armstrong did at Cragside on a small scale at a beach near me by pumping seawater up an incline to be released through turbines when it's needed, or does the physics not work?
Oh, the physics works. Who's going to answer this? Okay, the physics works fine, and it's what we use at Denolwick. I think that was mentioned by one of the, I think it was mentioned by Douglas in the first session. At Denolwick in North Wales, and a location in Scotland, when the power is not required for the grid, it's pumped, the water is pumped uphill and then brought down through turbines and allowed to then put power back into the grid when it's needed. It's a very, it's a very old piece of technology. Basically, it's a water wheel. I suppose the overall piece is it's quite hard work. Gravity is a weak force, and only Frank works on planet-sized and larger bodies to any great effect. So it's not especially efficient. But yes, of course. Yeah. Anybody want to add to that? Yes. Well, let's open up the commentary a bit wider now.
John Giles, Weir Valley. It's probably related to both Gavin and Frank, this one. With the advent of Brexit, sorry, don't all shudder at once. With the advent of Brexit, is such things as the ITER project a bit vulnerable?
Not really. The UK government is committed to keeping involved in it and paying for it, so no. The one thing I did notice when I visited the Culham Centre for Fusion Energy is because we have so much experience in remote handling, I think they're trying to pitch that this will be the next big industry. So you can't go inside the vessel when plasma's on or when it's off. So they have robotic arms. So I think they think that this will be a big industry that we can sell to the world.
The gentleman with the blue.
Just a quick question. Alan Morrison, Dunelm U3A. Given that gas is going to be around for a while yet, what represents the biggest risk? Is it transporting liquefied natural gas at minus 162 degrees halfway around the world, or is it fracking wells locally? I've got to declare an interest here, and that's meant 30 years fracking wells, but never mind.
There might be other factors in there as well. Kevin, do you want to?
Yeah, fascinating question, and of course it's one that's right at the centre of UK energy policy at the moment. What role expanding domestic gas supply through fracking can have in addressing energy security concerns. Where to begin? So one way that you can start to think about these two different sources of gas is to think about their carbon emissions. And there's some interesting work looking at the life cycle emissions of fracked gas and gas that has been brought to the surface by conventional means in Qatar or Norway and then brought long distance in these ships. And it's clear that the LNG chain does have significant CO2 emissions, as well as the problem of leaking methane. In the gaseous form. But so too does fracking. And there's a lot of uncertainties around fracking. So if the argument is a straight match-up of CO2 and greenhouse gas contributions, there's no straight answer to that. I think, though, with the fracking side of it, we've got a series of additional environmental concerns that tend to centre on water, although it's not exclusively about water. There's also a concern that this is actually unlike conventional oil and gas, where essentially you stick a spike in the ground and the materials come out. This is not a plug-and-play thing. You've got to keep hitting the formation in order to get the flow rates that you need. So the profile of a fracked well is very different to conventional oil and gas. It's more like an industrial site, where you need frequent deliveries of trucks and materials to get those flow rates. And then you've got technical concerns about the uncertainties of flow rates from fracked wells. And beyond that, there's then a set of concerns about actually would fracking in a UK context add to energy security? And it's not clear at all that it would, because quite a lot of that gas might just simply exit the UK through the pipeline systems that we have. Those pipelines to Europe run both ways. So I think your question is a really important one, is to help, it's encouraging us to think through what is the environmental and security profiles of these different sources of gas and what role can they play. Yes, and so the response to that, the industry's response to that is something like 80,000 port calls over the last 10 years or something, and no significant incidences. They point out that yes, you have a very large amount of energy confined in a ship, and that if something were to go wrong, then the prospect of that being catastrophic is significant. But they also point out how it's not like oil spills, that this stuff dissipates and diffuses quite rapidly. So there are arguments on both sides of that. And in a way, we're comparing different forms of risk as well. Thank you.
I spent 28 years in the petroleum industry before joining Durham in 2009, so I'm going to also add my two penneth. I think there is a third way here, to borrow a phrase from a few years ago. The UK has recognised over the last couple of decades what was about to happen in 2004, that we would need to start importing gas. But it's reacted to it in a rather peculiar way. It's seen, and the same is true of Poland, for example, it's seen the immense success of the US in terms of fracking and said, we would like some of that. But the US got to the stage it has now with these big shales, which are being fracked across the states with tens to 100,000 wells or so, by going through several stages. And the first stage it went through after conventional gas is what's called tight gas. Now, in a shale gas, you've got very little gas in a very large volume of shale. In a conventional reservoir, you've got a lot of gas in a porous sandstone, rather like on the beach or so. And in a tight gas, you're somewhere in between the two. The storage capacity is quite high, but the flow potential is low. It's still about 10,000 times better than shale gas, but it's low. In the North Sea, there are at least 100 discoveries of tight gas which have not been developed. And the last job I did before joining this university was to buy a field which had sat undeveloped for nearly 40 years from Shell and Esso for £5 million. We multi-fracked it, and it's one of the best producers in the North Sea now. There are huge resources untapped there, which do not require anything like the same sort of intense activity you would need to do onshore. And yet, despite telling 3 of the energy ministers about the opportunities here, only now is the new Oil and Gas Authority beginning to listen. And they've said to me, hang on, we've not yet appointed our tight gas person. When we do, we'll give you a call. So, there's a momentum here. They've seen, if you like, the sexy, in terms of economic sense, and I'm standing away from the environmental piece at the moment, they've seen what appears to be a very sexy outcome in the USA, and I'll look at it again this afternoon, if I may. So we do, I think as someone said earlier on, there is not a shortage of accessible energy. It's just, it's up here where some of the problems lie. What I'm going to do now as chair is say, we all probably need a little energy. And so we will have lunch now, and we'll reconvene and do a bit more. Thank you.